Welcome to Introduction to Modern Neural Networks. After watching this video, you will be able to explain the key characteristics and purposes of major modern neural network architectures and compare transformers with earlier neural network approaches. Recognizing images involves analyzing large amounts of visual data. However, tasks that once took hours with early models can now be completed in minutes or even in real time using modern neural networks with much higher accuracy. This highlights how neural networks have evolved from simple single-layer models to the deep and specialized architectures used today. Let's begin by understanding transformers, a major shift in neural network design that underpins modern deep learning, especially large language models. Unlike recurrent networks that process sequences step by step, transformers use attention mechanisms to consider all elements of a sequence at once, enabling efficient modeling of long-range dependencies. Because attention can be computed in parallel, they scale extremely well on modern hardware. Transformers stack attention layers with feed-forward networks to learn rich contextual representations and are now widely used beyond language, including vision, speech, and multimodal tasks. Deep feed-forward neural networks build on the idea of basic neural networks by using multiple hidden layers instead of just one. In these models, information flows in a single direction from input to output, without cycles or feedback connections. As data moves through the layers, the network learns increasingly abstract representations. For example, when processing images, early layers may detect simple patterns such as edges, while deeper layers combine these into shapes and objects. This hierarchical feature learning allows deep networks to capture complex, nonlinear relationships that shallow models cannot. However, greater depth also introduces challenges, including vanishing gradients, longer training times, and sensitivity to initialization. Modern training techniques such as improved activation functions, normalization, and advanced optimizers help make these networks more stable and practical. Deep feed-forward networks also serve as the foundation for many other architectures, including convolutional networks and transformers. Convolutional neural networks, or CNNs, are specialized neural networks designed for grid-like data, most commonly images. Unlike standard feed-forward networks, CNNs take advantage of the spatial structure of the input. They use convolutional layers that apply small filters across an image to detect local patterns such as edges, textures, and corners, while sharing parameters to reduce complexity. Pooling layers help reduce spatial size while preserving important features. By stacking multiple layers, CNNs learn increasingly complex visual representations from simple patterns to objects. This structure makes them highly effective for tasks such as image classification, object detection, and medical image analysis, demonstrating how architectures can be tailored to specific data types. Recurrent neural networks, or RNNs, are designed for sequential data such as text, speech, and time series, where order and context matter. They maintain a hidden state that evolves over time, allowing the output at each step to depend on both the current input and previous information. This enables RNNs to model temporal dependencies across sequences. However, standard RNNs struggle with long-term dependencies due to vanishing gradient problems. To address this, advanced variants were developed. Long short-term memory, or LSTM networks, use gating mechanisms to control what information is stored, forgotten, and passed forward, enabling learning over longer sequences. Gated recurrent units, or GRUs, simplified this design while retaining similar performance. These models have been widely used in language modeling, translation, speech recognition, and time series forecasting. So, how do these architectures fit together? Each type of neural network reflects a response to specific data and modeling challenges. Deep feed-forward networks provide the foundation for learning complex nonlinear functions. CNNs build on this foundation to handle spatial data by leveraging local structure, while RNNs, LSTMs, and GRUs extend neural networks to sequential and temporal data. Transformers take this further by enabling scalable sequence modeling through attention-based computation. Together, these architectures represent the evolution of neural network design toward greater expressiveness, efficiency, and scalability. In this video, you learn that transformers use attention mechanisms and parallel processing to model sequences more efficiently than earlier approaches. Deep feed-forward networks provide the foundational structure for learning complex nonlinear relationships through multiple layers. Convolutional neural networks specialize in spatial data, such as images, while recurrent architectures, such as RNNs, LSTMs, and GRUs, are designed for sequential data. Together, these architectures represent the evolution of neural networks toward greater expressiveness, efficiency, and scalability. Welcome to Introduction to Matrices and Vectors. After watching this video, you will be able to define vectors and explain their role in linear transformations, and explain basic vector operations geometrically and in machine learning contexts. Think of a vector as an arrow that shows magnitude and direction. Now imagine a matrix as a machine that takes that arrow and changes it by rotating it or stretching it. Together, they help us describe movement and change. Let's look at how this works. Before diving deeper, let's learn about vectors and matrices within a broader mathematical hierarchy. A scalar is a single numerical value, such as temperature or learning rate. A vector is a one-dimensional array of numbers. A matrix is a two-dimensional array of numbers. A tensor is a more general structure that extends beyond two dimensions. Now, let's look at vectors and matrices as linear transformations. Vectors are mathematical objects defined as ordered collections of numbers that represent a point, direction, or quantity in space. In 2 or 3 dimensions, they appear as arrows, while in higher dimensions, they capture abstract quantities, such as feature values in a dataset. Vectors represent input features, weights, and parameters, and gradients during optimization. Now let's look at matrices as transformations. A matrix acts as an operator that transforms vectors. When a matrix multiplies a vector, it produces another vector, a process known as a linear transformation. Linear transformations preserve linear structure, meaning straight lines remain straight and proportional relationships remain consistent. Common transformations include scaling, which changes vector length, rotation, which changes orientation, reflection, which flips vectors across an axis, and shearing, which skews space. In machine learning, matrices transform input data into new representations that simplify learning and improve model performance. Now let's look at basic vector operations. Vector addition combines two vectors by adding their corresponding components. Geometrically, it represents the combined effect of two movements or displacements in space. Scalar multiplication involves multiplying a vector by a single number. This operation changes the vector's magnitude while preserving its direction, and a negative scalar reverses the direction. Scalar multiplication is widely used in feature scaling, normalization, and gradient updates. The inner or dot product takes two vectors and produces a scalar. It measures how aligned the vectors are. A positive value indicates a similar direction. A 0 indicates perpendicular vectors, and a negative value indicates opposite directions. Dot products are commonly used to compute angles between vectors, to project vectors, and to assess similarity in machine learning models. The outer or dyadic product produces a matrix from two vectors, where each element of the matrix represents the interaction between components of the vectors. This operation is important in constructing covariance matrices, modeling feature interactions, and building neural network weights. Dual vectors, also called covectors, represent linear functions that map vectors to scalar values. While vectors describe quantities or directions, dual vectors describe measurements applied to those vectors. A common example is the dot product with a fixed vector, which assigns a scalar value to any input vector. Dual vectors are especially important in coordinate systems, projections, and optimization algorithms. Gradients are naturally expressed as dual vectors because they describe how a scalar loss function changes with respect to vector inputs. And understanding this distinction deepens intuition around learning algorithms and backpropagation. Now, let us look at the geometric interpretation of vector and matrix operations. Geometric intuition plays a key role in understanding linear algebra. Vector addition combines movements, while scalar multiplication stretches or shrinks vectors. The dot product measures projection and alignment. Matrices reshape space through transformations, and applying a matrix to multiple vectors shows how the entire space is transformed. Some transformations preserve distances and angles, while others distort them. These concepts are central to understanding feature transformations, dimensionality reduction, and decision boundaries in machine learning. In this video, you learned that a vector is an ordered collection of numbers representing a point, direction, or quantity in space. A matrix is a two-dimensional array of numbers that transforms vectors through linear operations. A scalar is a single numerical value, and a tensor generalizes vectors and matrices to higher dimensions. Vector operations include addition, scalar multiplication, dot product, and outer product, describing movement, alignment, and interactions. And dual vectors map vectors to scalars, and geometric interpretations help visualize transformations, feature mappings, and dimensionality reduction in machine learning. Welcome to Introduction to Tensors and Datasets in PyTorch. After watching this video, you will be able to explain tensors and basic tensor operations in PyTorch and describe gradient computation and dataset handling in PyTorch. Imagine trying to teach a robot to recognize a cat in a photo. Before it can learn anything, the image must be converted into numbers the computer understands. In PyTorch, these numbers are stored in tensors. Tensors act like the language neural networks use to read data, perform calculations, and learn. Without tensors, deep learning models simply couldn't function. Now, let's look at tensors as the building blocks of neural networks. A tensor is a multidimensional array that generalizes scalars, vectors, and matrices. A scalar is a zero-dimensional tensor, a vector is one-dimensional, and a matrix is two-dimensional. Higher dimensional tensors represent structured data such as images, sequences, and batches of samples. In neural networks, tensors are used at every stage of computation. Input data, such as features or images, are stored as tensors, and model parameters, such as weights and biases, are also tensors that get updated during training. The network's outputs, including predictions and probabilities, are also tensors. In PyTorch, tensors are similar to NumPy arrays, but support automatic differentiation and can run on CPUs or GPUs for efficient deep learning computation. Now let's dive into tensor operations, which are the basic computations used in neural networks. These operations include arithmetic, indexing, slicing, reshaping, and linear algebra. Vector and matrix operations are particularly important because many neural network layers depend on linear transformations. For example, matrix multiplication combines input tensors with weight tensors in layers, such as fully connected layers. Element-wise operations are used to add biases and apply activation functions. PyTorch also supports broadcasting, which allows tensors with different shapes to interact without manual reshaping. In addition, reshaping operations like reshape or view are often used to prepare data for different layers, such as flattening image tensors before passing them into dense layers. Efficient tensor operations enable quick processing of large batches of data during training. Next, let's look at derivatives and gradients, which are essential for training neural networks. During training, the goal is to minimize a loss function that measures the difference between the model's predictions and the actual target values. To do this, the model needs to understand how changes in its parameters affect the loss. A derivative shows how a function changes with respect to a variable, while a gradient represents these changes across multiple parameters. In neural networks, gradients indicate how each weight or bias influence the loss. PyTorch makes this process easier through its automatic differentiation system called AutoGrad. As operations are performed on tensors that require gradients, PyTorch records them in a computational graph. When the backward function is called on the loss, PyTorch automatically computes the gradients using the chain rule, and these gradients are then used by optimization algorithms to update the model's parameters. Next, let's look at data conversion and tensor management. In most machine learning projects, data comes from external sources such as files, databases, or data processing libraries. Before this data can be used in a neural network, it must first be converted into tensors. PyTorch makes this process straightforward by allowing easy conversion from Python lists and NumPy arrays into tensors. It is also important to manage tensor shapes and data types carefully, since the input data must match the dimensions expected by different neural network layers. In addition, PyTorch allows tensors to be moved between CPUs and GPUs, enabling hardware acceleration and improving training performance, especially when working with large models and datasets. Finally, let's look at the dataset class for handling large datasets. In real-world deep learning projects, datasets can be very large, and loading the entire dataset into memory is often not practical. PyTorch provides the dataset class as a standard way to efficiently manage and access data. Instead of loading all data at once, a dataset object defines how individual samples are retrieved as needed. For example, in image classification tasks, dataset information may be stored in a file that lists image paths and labels. The dataset class reads this information and loads each image only when a specific index is requested. Typically, a dataset implementation includes one method that returns the total number of samples and another that retrieves a particular sample and its label. This approach allows large datasets to be handled efficiently without loading the entire dataset into memory at once. In this video, you learned that tensors are the core data structure in PyTorch, representing data, model parameters, intermediate computations, and outputs in neural networks. A tensor is a multidimensional array that generalizes scalars, vectors, and matrices and is used to represent structured data such as images and batches of samples. Tensor operations such as arithmetic operations, matrix multiplication, reshaping, and broadcasting enable neural networks to perform computations efficiently. Gradients and automatic differentiation help train neural networks by computing how model parameters affect the loss and updating them during optimization. And efficient data handling in PyTorch includes converting data into tensors and using the dataset class to access large datasets without loading everything into memory. Welcome to Understanding 1D Tensors in PyTorch. After watching this video, you will be able to explain what 1D tensors are, describe how 1D tensors are created and accessed, understand how data types and sizes are handled, explain how type conversion and reshaping works, and understand how 1D tensors interact with NumPy and pandas. One-dimensional, or 1D tensors, are the most basic tensor structure in PyTorch and serve as the foundation for numerical computation in deep learning workflows. In neural networks, 1D tensors are frequently used to represent input features, model or bias parameters, weight vectors, and flattened representations of higher dimensional data. A solid understanding of 1D tensors is essential before working with higher dimensional tensors used in neural networks. A 1D tensor is an ordered set of numerical values arranged along a single dimension. It is equivalent to a vector in linear algebra or a one-dimensional array in programming. Therefore, you will also often see 1D tensors referred to as vectors or arrays. Each element is accessed using a single index, and all elements in the tensor share the same data type. PyTorch supports different data types for 1D tensors depending on the use case. Commonly used 1D tensor data types include floating point tensors for numerical computation, integer tensors for discrete values, and byte tensors for raw or binary data. Choosing the appropriate data type is important because it affects memory usage, computational efficiency, and numerical precision. PyTorch provides multiple methods for creating 1D tensors. One common approach is creating a tensor directly from a Python list, which is intuitive and useful for small data sets or demonstrations. Other commonly used creation methods include creating tensors filled with zeros or ones for initialization, creating tensors with random values for parameter initialization, converting NumPy arrays into PyTorch tensors. These methods allow developers to generate tensors that match specific initialization and shape requirements. Elements of a 1D tensor are accessed using indexing. Indexing follows standard Python conventions, starting from 0. This makes it easier to retrieve or modify individual elements. Slicing allows access to a contiguous subset of elements within a tensor. A slice operation returns another 1D tensor containing the selected values. Slicing is efficient and avoids unnecessary data copying. Indexing and slicing are essential for tasks such as feature selection, data preprocessing, and debugging intermediate computations. Every tensor in PyTorch includes metadata that describes its structure. Two key properties are data type and size. The data type specifies how values are stored and how computations are performed. Floating point tensors support gradient computation and are typically used in neural network training. Integer tensors are often used for indexing or categorical data. The size of a 1D tensor represents the total number of elements it contains. Ensuring that tensor sizes match expected dimensions is critical when passing data through neural network layers. Size mismatches are a common source of runtime errors. Regularly inspecting data types and sizes helps maintain correctness and stability in machine learning pipelines. Type conversion refers to changing the data type of a tensor. This is often necessary when preparing data for neural network training. For example, integer inputs usually need to be converted to floating point format before being used in gradient-based optimization. PyTorch provides explicit methods for typecasting, allowing tensors to be converted efficiently and safely. Type conversion creates a new tensor with the desired data type while preserving the numerical values as closely as possible. This step is particularly important when working with data from external sources, where formats might not align with model requirements. Although 1D tensors are useful, many neural network layers expect inputs in 2 dimensions. PyTorch allows reshaping of tensors without copying data, provided the total number of elements remains unchanged. The view operation is commonly used to reshape a 1D tensor into a 2D tensor. For example, a vector can be reshaped into a matrix with 1 row or 1 column. This operation changes how the data is interpreted while preserving the underlying values. Reshaping is frequently used when preparing inputs for batch processing or transitioning between different network layers. PyTorch is designed to integrate smoothly with commonly used data processing libraries. 1D tensors can be converted to NumPy arrays and back with minimal overhead. This allows developers to use NumPy for pre-processing and PyTorch for model training. Similarly, data stored in pandas series objects can be converted into 1D tensors. This is especially useful when working with tabular data sets where pre-processing is often performed using pandas. This interoperability enables flexible and efficient data pipelines in real-world machine learning workflows. In this video, you learn that a 1D tensor is a single-dimensional array of numerical values. PyTorch supports multiple data types and flexible creation methods. Indexing and slicing enable efficient access to tensor elements. Inspecting size and data type ensures compatibility and correctness. Type conversion prepares data for neural network computation. Reshaping allows adaptation to layer input requirements. And integration with NumPy and Pandas supports practical data workflows. Welcome to Common Operations in 1D Tensors using PyTorch. After watching this video, you will be able to describe the common types of operations performed on 1D tensors, apply universal functions to 1D tensors to simplify numerical computations, and use the linspace function on 1D tensors to generate evenly spaced values for plotting and analysis. One-dimensional tensors are widely used in PyTorch to represent vectors, model parameters, and intermediate values in neural network computations. Beyond creation and indexing, understanding how to perform operations on 1D tensors is essential for data processing, mathematical modeling, and machine learning workflows. These operations form the basis of linear algebra computations used throughout deep learning models. Vector addition is one of the most fundamental operations performed on 1D tensors. It involves adding corresponding elements of two tensors of the same size to produce a new tensor. Vector addition requires both tensors to have the same size. If the sizes do not match, the operation is invalid unless broadcasting rules apply. Each position in the output tensor is the sum of the elements at the same position in the input tensors. This operation is commonly used when combining feature vectors, accumulating gradients, or updating parameters during training. From a mathematical perspective, vector addition represents combining two directions or quantities. In machine learning, it is often used to combine learned representations or apply incremental updates. Scalar multiplication involves multiplying every element of a 1D tensor by a single numerical value. This operation scales the tensor uniformly and preserves its structure. Scalar multiplication is widely used in data normalization, learning rate application, and parameter updates. For example, gradients are often multiplied by a learning rate before being applied to model parameters. The scalar multiplication operation is efficient and applies element-wise across the tensor, producing a new tensor with scaled values. The Hadamard product, also known as element-wise multiplication, multiplies corresponding elements of two tensors of the same size. Unlike the dot product, which we'll discuss next, the result is another tensor rather than a single scalar. Key characteristics of the Hadamard product include: both tensors must have the same size or be broadcast compatible. Multiplication occurs independently at each index. The output tensor has the same shape as the input tensors. The Hadamard product is frequently used in feature weighting, masking operations, and neural network layers where element-wise interactions are required. The dot product is a fundamental operation that takes two 1D tensors of equal length and produces a single scalar value. It is computed by multiplying corresponding elements and summing the results. The dot product measures the degree of alignment between two vectors. A large value indicates stronger alignment, whereas a value close to zero indicates little or no correlation. In machine learning, the dot product is central to linear models, fully connected neural network layers, similarity measurements between vectors. The dot product reduces a vector interaction into a scalar, which is often used as input to activation functions or loss calculations. Broadcasting enables PyTorch to perform operations between 1D tensors of different sizes by automatically expanding one tensor to match the size of the other. Broadcasting follows strict rules to ensure consistency. When applied correctly, it eliminates the need for manual reshaping and simplifies code. Common use cases include adding a scalar to every element of a tensor, multiplying a tensor by a smaller compatible tensor, applying bias terms efficiently. Broadcasting improves readability and performance, but requires careful attention to tensor sizes to avoid unintended behavior. PyTorch provides a wide range of universal functions that operate element-wise on tensors. These functions are optimized for performance and can be applied directly to 1D tensors without explicit loops. Common universal functions include trigonometric functions such as sine, reduction operations such as mean and maximum, and mathematical transformations applied element-wise. The sine function applies a trigonometric transformation to each element independently. This is useful in signal processing and mathematical modeling. The mean function computes the average value of all elements in a tensor, producing a scalar. It is commonly used in loss functions and data analysis. The max function returns the largest value in the tensor. It is frequently used in normalization, thresholding, and decision-making logic. These functions simplify numerical computation and improve code clarity. The linspace function is used to generate a 1D tensor containing evenly spaced values over a specified range. It is especially useful for numerical experiments, function evaluation, and plotting. Linspace is commonly used when generating input values for mathematical functions, creating smooth curves for visualization, and sampling values uniformly over an interval. In plotting scenarios, linspace is often combined with universal functions such as sine or cosine to visualize mathematical relationships. The resulting tensors can be converted to NumPy arrays and passed to plotting libraries. Linspace ensures consistent spacing between values, which is important for accurate analysis and visualization. In this video, you learned that one-dimensional tensors are used in PyTorch to represent vectors, model parameters, and intermediate values. Operations form the basis of linear algebra computations used throughout deep learning models. Vector addition adds the corresponding elements of two tensors of the same size to produce a new tensor. Scalar multiplication multiplies each element of a 1D tensor by a single numerical value. The Hadamard product multiplies corresponding elements of two tensors of the same size. The dot product takes two 1D tensors of equal size and produces a single scalar value. Broadcasting enables PyTorch to perform operations between 1D tensors of different sizes by expanding one tensor to match the size of the other. PyTorch provides universal functions that operate element-wise on tensors. Common universal functions include trigonometric functions such as sine, reduction operations such as mean and maximum, and mathematical transformations. And the linspace function is used to generate a 1D tensor containing evenly spaced values over a specified range.
Yeah.